Hello, my name is Andrew Rizhikov and I'm presenting the talk The Degree of a Finite Set of Words. This is a joint work with my PhD advisor Dominic Perron. In our work, we are motivated by the following notion of a synchronizing set of words. Let X be a set of finite words, and I have to say that in my talk I will assume all words to be finite. Then a word W is called synchronizing for X if for any words U and V such that the whole concatenation UWV is a concatenation of words from X, we also have that UW and WV are in X star. A set having a synchronizing word is also called synchronizing. This notion is motivated, for instance, by this particular usage. If we have some long message of words from X, and we see a synchronizing word W occurring there twice in a row, then we can partition this long message into two smaller ones, UW and WV, and we can decode them independently. Thus we can make the decoding process easier, and for instance we can parallelize it. Let's look at some examples. The word ABA is synchronizing for the set AABA. This is quite obvious because every time we see ABA, we know that it is the second word from our set. The set of all words of length 2 over a binary alphabet is not synchronizing. To see it, suppose that W is a synchronizing word for this set. If the length of W is even, we can take two arbitrary words U and V of odd length. Then the length of UWV is even, so it is a concatenation of words from X, but the length of the words UW and WV are odd, so they do not belong to X star. The case where the length of W is odd can be treated similarly. The notion of synchronization is mostly studied for uniquely decipherable codes or just codes. A set X of words is called a code if no word can be represented as a concatenation of words in X in two different ways. For example, the set AABA is a code because if we have a concatenation of words from this set, every time we see B, we know that this is an occurrence of the word ABA, and the rest are occurrences of the word A. The set ABBA is not a code, since for the word ABABA we have two different partitions into words from this set. A powerful tool to study codes and sets of words in general is a composition of sets. Let Y and Z be two finite sets of words, Y over the alphabet B and Z over the alphabet A, such that there exists a bijection beta from B to Z. This means that the size of the alphabet of Y is the same as the number of words in Z. Two such sets are then called composable, and we define the composition of these two sets as just the image of Y under beta, where we take beta to be naturally extended to the mapping from B star to Z star. So this means that we take every word from Y and then substitute all letters there with the words from Z. We then say that X is a composition of Y and Z under beta, and we say that X is represented as a decomposition in such a way. Let's look at some example. We have two 3-word sets Y and Z here, and we have beta to send U to A, V to AB, and W to BA. In this case, we have their composition to be AABA. A particular class of decompositions is trim decompositions. A decomposition of X into Y and Z is called trim if every letter of the alphabet of Y appears in a word of Y, and every word in X is obtained in a unique way from words in Y. This means that the restriction of beta to Y is injective. Let's look again at our example. We can see that the decomposition here is not trim, since we can obtain the word ABA in two different ways, from the word UW and from the word VU. In fact, we can make our decomposition trim by removing some words from Y and Z. For example, we can remove the word VU from Y, thus we obtain the set Y prime over the alphabet UW, and then we have to remove the word AB from Z since it corresponds to the letter V, which is no longer used. For any decomposition, we can get a trim decomposition in this way by removing some words from Y and Z. Let's give a definition of a complete set. We say that a word W is a factor of a word X if X can be represented as UWV for some words U and V. A set X over the alphabet A is called complete if any word in A star is a factor of a word in X star. For example, the set ABABB is complete, and the set AABA is not complete since there is a word, for instance BB, which does not appear as a factor in any sequence of words from this set. Let me now describe the general goal of our work. Suppose that we decompose a finite set X into a composition of Y and Z, where Y is complete. Our goal is to define a number called the degree of X in such a way that the degree of X is 1 if and only if X is synchronizing, and the degree of X is at most the degree of Y times the degree of Z. This is already known for codes, and in the case of codes, we actually have equality instead of inequality. But as we will see in the general case of finite set of words, sometimes we have a strict inequality. To study sets of words with respect to a decomposition, we need a suitable class of automata. In our case, it's non-deterministic automata recognizing X star with multiplicities. Let A be a non-deterministic automaton, where Q is its set of states, I is an initial state, and T is a terminal state. In all my talk, I will use non-deterministic automata with a single initial and a single terminal state. Given a set X, we say that the automaton A recognizes X star with multiplicities if for any word W the number of paths from the initial state to the terminal state labeled by W is equal to the number of distinct factorizations in X. Let's look at an example. Suppose that X is a set of two words A and A squared over a unary alphabet. The number of factorizations of A to the n in words of X is the n plus first Fibonacci number, and the automaton A recognizing X star with multiplicities can be seen in the slide. And indeed we can see that if we're in the state 1 and we have at least two letters yet to read, then we can either make a loop to the state 1 twice, or we can go to the state 2 and then back to. For any finite set of words, there is always an automaton recognizing its star with multiplicities. One example of such automaton is the flower automaton of a finite set. It is built as follows. We take the state corresponding to the empty word, and then for every word from the set, we take a separate path from the state to itself. We then make the state corresponding to the empty word as the initial and the terminal state. Let's take a look at the example. We take X to be the set of words A, A, B, B, A, and as we can see, there is a self loop labeled by A, and there are two other paths labeled by A, B, and B, A. If we take, for instance, the word A, B, A, then it labels two different paths from the initial state to this state, which is also the terminal state, and this is in accordance to the fact that this automaton recognizes X star with multiplicities. A more compact version of the flower automaton is the prefix automaton of a finite set X. Its states are proper prefixes of words from X, and for every proper prefix P and a letter A, we have a transition to PA if PA is also a proper prefix of a word in X, and we have a transition to the state corresponding to the empty word if PA is a word in X. We make the state corresponding to the empty word as the initial and the terminal state of our automaton. We can see in the example the flower automaton and the prefix automaton for the set A squared and A cubed. Suppose that we can decompose a finite set X into a composition of y and z. We then need a tool which allows us to relate an automaton recognizing x star with multiplicities with an automaton recognizing z star with multiplicities. Such a tool is a reduction. A reduction from an automaton A onto an automaton B is a surjective map row from the set of states of A to the set of states of B, such that the initial and terminal states are preserved, and also for every pair of states of B and every word W, there is a path from Q to Q prime labeled by W in B, if and only if there is a path from P to Q prime labeled by W in A for some state and P prime of A, such that row of P equals Q and row of P prime equals Q prime. This means that we can lift every path in B to a path in A and vice versa. Let's look at an example. The left automaton here is A and the right automaton is B. If we pick a path labeled A, B, C, A in B, we can lift it to a corresponding path in A. Given two composable finite sets y and z, we can build their prefix automata. Then we can define the composition of this prefix automata. We define it in such a way that the resulting automaton recognizes the star of the composition with multiplicities. This proposition formally states that if we have two composable finite sets y and z, and x is their composition, then the composition of the prefix automata of y and z recognizes x star with multiplicities. Moreover, if y is complete, then there is a reduction from the resulting automaton recognizing x star with multiplicities onto the prefix automaton of z. Next, we will need the notion of the rank of a relation. Consider an automaton A and let W be a word. Let M of W be the relation on Q defined in such a way that the element PQ is 1 if and only if there is a path labeled by W from P to Q in A, and otherwise this element is 0. The rank of a relation M on Q then is the minimal cardinality of a set R, such that we can represent M as a product UV, with U a Q times R relation and V an R times Q relation. Equivalently, the rank of M is the minimal number of row vectors which generate over 0, 1 the set of rows of M, or which is the same, the minimal number of column vectors which generate over 0, 1 the set of columns of M. Let's come back to the automaton from our example. If we take the word CAAB and write down the matrix of a corresponding relation, then we get the following matrix. We can see that this relation is generated by two columns, the first one and the sixth one. So this relation has rank 2. We will be looking at the way how idempotents of minimum rank act on strongly connected components of their fixed points. A fixed point of a relation M on Q is an element Q such that M takes Q to itself. Let E be an idempotent relation on a finite set Q, and let S be the set of fixed points of E. By gamma we denote the set of strongly connected components of the restriction of E to S. The picture shows the action of the word CAAB on the states of the automaton from our example. We can see that the states 1 and 8 are fixed points, and we have two strongly connected components, one consisting just of the state 1 and one consisting just of the state 8. If we look at the action of the word CAAB square, then we have again two fixed points 1 and 8, but there is only one strongly connected component, since the state 1 is taken both to state 1 and state 8, and the state 8 is taken both to state 8 and to state 1. Now we are looking at the H-class of an element of a monoid. It is a group if and only if it contains an idempotent. Let once again M be a monoid of relations on a finite set Q, E be an idempotent, and gamma be the set of strongly connected components of the fixed points of E. Then there is an isomorphism between the H-class of E and a group of permutations on gamma. We denote G sub E this group of permutations. As I've said, in our example of the action of CAAB square, we have two fixed points 1 and 8, and only one strongly connected component containing both 1 and 8. In this case, the permutation group that we get is trivial. Two permutation groups are called equivalent if their group actions are isomorphic. The next proposition states that if we have a monoid of relations M on a finite set Q, and we have two D-equivalent idempotents E and E prime, then the groups G sub E and groups G sub E prime are equivalent permutation groups. Let M be a monoid of relations on a finite set Q. M is called transitive if for every P and Q there is an element M mapping P to Q. The minimal rank of M is the minimum of the ranks of the elements of M other than 0. Let M be a transitive monoid of relations on a finite set Q. The set K of elements of minimum rank is a D class and always contains an idempotent. The groups G sub E for E and idempotent in K are equivalent transitive permutation groups. This means that whichever idempotent of minimum rank we take, we always get an equivalent permutation group. The Suschkevitch group of M is one of the equivalent groups G sub E for E of minimum rank in M. Now we are ready to define two invariants of a finite set X of words. Let A be the flower automaton of X. The degree of X is then the minimal rank of the monoid of transitions of A. The group of X is the Suschkevitch group of this monoid. We prove that the definitions of the group and the degree do not depend on a particular trim automaton recognizing X star with multiplicities. This means that they are indeed the invariants of a finite set of words. Now we can finally formulate our main results. First, we prove that a finite set of words is synchronizing if and only if its degree is 1, and then we show that if X is a finite set of words and there is a trim decomposition of X into Y and Z where Y is complete, then we have the inequality that the degree of X is at most the product of the degree of Y and the degree of Z. To show that, we look at the actions of the groups of X, Y, and Z and the relations between them. Let's come back to our example. We have the set Y, which is all the words of length 2 over the alphabet U, V, W, X, and this set has degree 2, and the set Z consisting of the words A, B, B, C, C, A. This set has degree 1, and actually the word C, A, B is synchronizing for it. Their composition is the set X, which is the square of the set Z, and this set is synchronizing, and the synchronizing word for it is CAAB squared. So we can see that the degree of X is 1, even though the product of the degrees of Y and Z is 2. So we have a strict inequality in this case. Finally, I would like to mention the following result. One may ask if we get anything new when we start with a trim decomposition of a finite uniquely decipherable code, but let Y and Z be arbitrary finite sets of words. We show that this is not the case if Y is complete, namely, in this case we get that Y and Z are necessarily uniquely decipherable codes. And I would like also to mention that the fact that Y is complete is necessary in this proposition.